All right, welcome, ladies and gentlemen. Welcome back to our lessons. We're going to start in today at 2.7. We're going to try to finish up chapter 2 so we can get into the trigonometry, the more enjoyable stuff to me. All right, so we are going to finish this off. Today is 2.7, then we're going to finish 2.8 and 2.9 a little bit later in the week and next week, and we will complete our chapter 2 finally. So today, looking at graphing rational functions. So some of the stuff you might recall from last year from your Algebra 2 class, mainly basically what is a rational function? Well, a rational function is one that looks like this. You have an f of x divided by a g of x, and both of those functions are polynomials. So if you're doing a polynomial over a polynomial, you have a rational function. You might remember that in order to find the domain of a rational function, you have all real numbers except your vertical asymptotes, and that's except anything that makes the denominator equal to 0. Sometimes you don't have vertical asymptotes, but that's a very rare occasion in some of the stuff that we're doing today. Now, we've gone over this. We did this in the chapter 1, so this should be somewhat familiar to us. And the range is mostly restricted by horizontal asymptotes. And the thing that you have to remember is how to find horizontal asymptotes. Things like if the degree of the numerator is equal to the degree of the denominator. So if the degree of the numerator equals the degree of the denominator, that implies the horizontal asymptote is the ratio of leading coefficients. All right, so we call it A over B, the ratio of leading coefficients. If the numerator is less than the degree of the denominator, that implies the horizontal asymptote of y equals 0. And we're going to get to what happens. Now, we said before that if the numerator's degree is bigger than the denominator's degree, there is no horizontal asymptote. And we always just left it at that. Now, that's still true, but we're going to get these things called slant asymptotes. We can get asymptotes that are not horizontal or vertical. And that's what we're going to be looking at today quite a bit. So one thing I want to show is kind of some simple graphs, simple rational functions, ones where you have a linear function over a linear function. No quadratics or cubics just yet. And what we can do is we can actually we can describe it using transformations, like up 2, left 3, vertical stretch by 2, and all that sort of fun stuff. And something I'm going to note here, and it's kind of the degree, but it's also kind of if the numerator is just bigger than the denominator. Or greater than or equal to. I said equal to here. Okay? So if the degree of the numerator is greater than or equal to the degree of the denominator, then we can use polynomial division, like long division, to rewrite the rational function. So first, I want to look at k of x. So k of x... if we said h of x is 1 over x, I can rewrite this function as 2 times the fraction 1 over x plus 3, which would actually be 2 times h of x, but it's h of x plus 3. And if we rewrote it like this, h of x plus 3 is going to be x plus 3 in the denominator, times 2, we'll put that 2 in the numerator, so we get this function. This means that it's left 3 units, and vertical stretch by 2. All right, so we can rewrite this as a transformation problem. But the little bit harder ones here would be ones like this. If I had 3x minus 7 over x minus 2. You might think, oh, it's being shifted to the right 2 units. Well, it is. But this 3x minus 7 is kind of a pain right now. So what I want to do is I want to divide that out. So I'm going to say x minus 2, and I'm going to divide that in to 3x minus 7. If I multiply by 3, oops, not 3x, just a 3, I get 3x minus 6. If I subtract, I get a minus 1. That means this fraction can be written as 3 minus the 1 over the x minus 2. Now, it might remember that we did this before. We called this a summary statement. But this now shows us transformations of 1 over x. I can write this as actually h of x minus 2, but it actually should be negative. And I'm going to add 3 on the outside. And if we looked at that, that means 3x minus 7 over x minus 2 is actually the function 1 over x moved up 3 units, left 2 units, and reflected across the y-axis. So we can rewrite these linear rational functions as some sort of transformation of the original function, or the parent function, just using long division and one of our summary statements from earlier in this chapter. But what I really want to get at are these end behavior asymptotes. Now, you remember that end behavior is stuff that's happening on either end of a graph. So given some sort of graph like this that goes like this, and let's say it goes like this, I don't care what goes on in the middle. Let's say it has an asymptote that looks like this at y equals 2. My end behavior asymptote would basically be y over 2, or y equals 2. But that's only for horizontal asymptotes. But let's look at what happens if the degree of the numerator is greater than the degree of the denominator. If that's the case, we're going to use division to find the asymptote. And we're going to get some really funky asymptotes. We're going to get diagonal asymptotes. We're even going to get a quadratic asymptote coming up here. So let's first look at x cubed over x squared minus 9. Now, obviously this denominator factors to x plus 3 and x minus 3, but that doesn't really help us just yet. What I want to do first is I want to divide using long division. So I got x cubed, I have 0x squared, I have 0x plus 0, and I'm going to divide in x squared minus 9. So I need to multiply by x. I get x cubed minus 9x over here, because I got to connect like terms here. And I'm going to subtract. That should be a cube. Subtract, no more x squareds, and I get a negative 9x. Or sorry, I'm subtracting. That's a plus 9x. See, I make errors too. And that's all the farther I get, huh? All right, so that means I can rewrite this function as x plus 9x over x squared minus 9. Okay, so now what happens? This right here is your slant asymptote. So when I go to graph, and we go to put on some asymptotes here, let's change pen color. Let's go to green. If we were to put in that asymptote, the slant asymptote of x. Okay, so y equals x looks like this. And we also have vertical asymptotes of 3 and negative 3. Okay, so we're going to go to 3 and negative 3. And we're going to get the graph to do some sort of funky little things going on here. So now we need to figure out how this function is graphed. I'm going to change my pen color one more time here. We're going to go to a blue. All right, if I was to plug in x equals 0 into the original function, I would get out a 0. That means it's going to go through the origin. But I really need to know what's going on at the asymptotes. So as x gets closer to 3 on the on the left-hand side of 3, I can basically plug in a number really close to 3 that's on the left-hand side. So I can say it's like positive 2.9. And if I plug in positive 2.9, I would notice that that answer comes out negative. So that means this is going to follow this asymptote like that. And if I plugged in something close to negative 3 on the right-hand side, I would say negative 2.9. I would find that that answer comes out positive, and it's going to follow my asymptote like that. But because there are two vertical asymptotes, that breaks my function into my graph into three separate spots. One in the middle, one on each side, and there's stuff that happens on these sides. If I plugged in, let's say, negative 3.1, I would also find that it's negative, which means this is going to come up here, and since we like to follow asymptotes, it's going to follow the asymptotes like this. And if I did the same thing up here, if I looked to 3.1, I would get something that is positive, and I would get a little piece of the graph that looks like this. And now we can graph all of these types of functions without needing a calculator. And that's the idea here, guys. I've told you guys this over and over again. The idea in my class is to try to get away from the calculator as being your crutch. It should just be a helpful tool, okay? So remember what we did here. We divided using long division. We put in our slant asymptote. In this case, it was just the linear function x. We put in any vertical asymptotes that we had. And from that, we then just started testing some points to see how my function was going to behave. Now, I'm not going to do the full analysis here, but you have to remember that analyze means to find the domain, find the range, find your asymptotes, and now we're going to start putting in slant asymptotes as well. Find minimums and maximums. You'll notice that the domain is everything except for 3 and negative 3. You'll notice the range is actually all real numbers. There is a maximum right here and a minimum right here. The only x or y intercept is the point 0, 0. And my end behavior is as x goes to infinity, y goes to infinity. And as x goes to negative infinity, y goes to negative infinity, following those asymptotes. Let's try a second one. Let's try 2x squared minus 2 over x squared minus 4. So I want to do some division first because the numerator is greater than or equal to. So I'm going to say x squared minus 4 going into 2x squared minus 2. So I have to multiply by 2. I get 2x squared minus 8. If I subtract, I get 6. So I can rewrite this function as 2 plus 6 over, I'm going to go ahead and factor here, x plus 2 and x minus 2. Now, normally we would call this a slant asymptote, but that doesn't have an x. And we might notice that since these two things had the same degree, it actually is just the 2, which is actually just a horizontal asymptote at y equals 2. So we have a horizontal asymptote at y equals 2. We have vertical asymptotes at both 2 and negative 2. And then I like to find any x-intercepts that we might have, or y-intercepts. If I plug in 0, I get, let's change the pen color here. If I plug in x equals 0, I get negative 1/2, or sorry, positive 1/2, which is, let's say, right about here. And if I find my x-intercepts, it's anything that makes the numerator 0, and that's going to be plus and minus 1. And really the only way that this function will work is if I go through these points, and doing a little test, we would notice that this goes down on the right-hand side of that asymptote, and it goes down on the left-hand side of that asymptote. And the only thing left would be to figure out what's going on these sides here. So we would test a point on the right-hand side of 2. So we'd say, okay, 2.1. We would notice that it's positive, and it's going to come in here like this. Remember, it can't cross the x-axis again, so it can't be down here. And we'll notice also, by doing a little test, that this part of the function graphs right there. I do want to make a note here on the range. The range of this function is going from negative infinity up until positive half, inclusive. And then it jumps. We can actually show, using a little bit of algebra, that there's nothing between positive half and 2. So we would start at 2 again and go up to infinity. I just want to make that note because people were kind of messing that up in the last chapter. Okay, I want to finish off with one more problem here, and it's this particular problem right here. Because I basically want to show a quadratic asymptote. So if we were to do the long division, x minus 1 into x cubed minus 3x squared plus 3x plus 1, we'd get x squared. So, okay, so x cubed, follow along here as I go ahead and do this. Minus that gets negative 2x squared. So I need to multiply by negative 2x. Subtract, I get x plus 1. And when I multiply by a 1, I get x minus 1. When I subtract, I get a remainder of minus 2. So this would look like now x squared minus 2x plus 1. And if you notice that, that is actually x minus 1 squared. That's going to come in handy. Minus 2 over, or sorry, that's actually a plus 2. Sorry, my fault. Plus 1 minus a negative 1. So that's a plus. X minus 1. So if we were to graph this, getting small down here, I would actually have a vertical asymptote at x equals 1. But weirdly, I also have a quadratic asymptote at x minus 1 squared. And that actually looks like this, because it's just the quadratic function moved to the right 1 unit. And doing some of our tests that we were just talking about, just testing some points close to our asymptotes, we would actually find, actually, sorry, we got to plug in some, find our y-intercept. Our y-intercept is negative 1, so that's kind of handy. And we'd actually notice that this function kind of comes down here like this, and like this. And then this piece kind of follows a little loopy thing there inside my quadratic asymptote. All right, so once again, it comes down to finding our asymptotes, plotting your intercepts, plotting your asymptotes, and then doing a little test to see where the function moves or where it goes. I'm going to leave you with this quote. You guys have an assignment sheet. We're going to continue working off that assignment sheet. So we're looking at 2.7. So have some fun with this. I hope you guys understood some stuff, learned some stuff. I'll see you guys tomorrow.